Okay, this is the second part of problem 428 in Young and Friedman for Physics 1607, Auburn University, fall 2013. And we just solved this problem. We drew a free body diagram of A in the last video where there was no friction between block B and the table. But part B of this problem says that assume now that there is friction between block B. So I'm going to erase this no. Now that there is friction, and it tells us exactly what that friction is. It says that the friction is exactly equal to the pulling force. In other words, this red vector here, this applied force, the friction between B and the table is going to be exactly, the magnitude is going to be exactly equal to that force. And so that's not going to change how I draw this system here, but it is going to change my free body diagram, because now I have to include that frictional force. And so the free body diagram I've drawn down here is still correct, but I need to add something to it. I need to add a frictional force. And as we have said before, frictional forces always oppose the motion. So this applied force F is going to make the system want to move to the right as I've drawn it. So the frictional force is going to be to the left, and I'm running out of room here. I'm going to call that F sub F, force of friction. And I haven't drawn it very well, but we're told the magnitude of this F sub F, let me change colors here. We're told that the magnitude here is exactly the same as the magnitude here. The direction is going to be opposite. So now, let's apply Newton's second law again to this. Again, in the y direction, notice I haven't changed anything, so we can safely assume it's still 0. There's no acceleration in the y direction. But let's see what happens in the x direction now. Sum of the forces in the x direction equals mass b times the acceleration in the x direction. So if I unpack this sigma, what I get is F minus the frictional force, F sub F. Lots of F's running around. These are different forces. This F is your applied force. This F is the frictional force that's trying to oppose the motion of the system. So, and the minus sign comes from the direction. We're told, and that's going to be equal to what? Well, we're told that F sub F and F have the same magnitude. So if they have the same magnitudes, when you subtract them, you're going to get a nice 0 over here, which means that A sub x equals 0. So we're still assuming that the system is in motion, excuse me, but now we're assuming that the acceleration is 0. In other words, we're moving at a constant velocity. We are, in fact, in equilibrium in the x direction and the y direction in this situation. So, if that is the case, let's see what happens to our free body diagram on A. So again, I'm going to do a free body diagram on A. Two-finger rule, gravity. So here's the weight of A. And whatever's touching it. And clearly block B is still touching it. Block B is still providing this normal force, which I'm calling F sub B, on block A. But now let's ask ourselves, do we have a frictional force between block A and block B? In the first part we did. And again, we're going to go, sorry, I should call this B, we're going to go to Newton's second law for the answer. Sum of the forces in the x direction equals ma sub x. So is there an acceleration? Well, when we looked on block B, we determined that there was no acceleration. And we're still assuming, because the problem has told us to, that block A and block B don't change their orientation with respect to each other. So what we have to conclude is that the left-hand side of this equation is 0. And if the left-hand side of this equation, then the net is 0, then the net force on, if the right-hand side of this equation is 0, then the left-hand side of this equation is 0. We have to conclude that the net forces acting in the x direction are 0, which means there is no frictional force. There are no other forces in the x direction, so if I added a frictional force, all of a sudden it would be non-zero. So we have to say that there is no frictional force acting between A and B. It might seem kind of strange to you, but if this is in equilibrium, that's exactly right. Okay.